technological innovations and their global implications. May I please request our esteemed panel to join us on the stage. Mr. Avinash Khare, who will be moderating the session with us, is ex-Tata Motors and consulting SME. May I have a round of applause, please? Joining him, we have Dr. Manoranjan Biswal, Senior Scientist, CIPET, SARP-APDDRL Bangalore. Welcome, sir. Mr. Lokesh Naik, MD and CEO, Durga Loykasts Private Limited. Welcome, sir. And Mr. Andrews Lejoy, Metal Application Leader, EOS GmbH, India. Thank you for joining us today, sir. Avinash, sir, may I request you to please take the session forward.
So, welcome for this session. We are going to talk about uh, the onslaught of technologies that are going to invade and they are going to transform the world of mold making. Okay. Now, mold making, of course, there are three parts. One is the plastics by themselves, plastic and plastic parts. So, Mr. Manoranjan will talk about the plastic part, questions related to the changes in plastics and like what changes are coming consequent to changes in plastic properties and stuff like that. Then we have the mold engineering person and finally we have the technology for additive manufacturing and 3D printing, how onslaught of 3D printing, particularly metal 3D printing, is going to transform this world of mold making. Now, by the way, when it was earlier plastic 3D printing, people started contemplating that one day it will kill molding itself because the plastic parts can be directly 3D printed, probably more economically. But then considering the speed of 3D plastic printing, if you compare it with the plastic molding, it's no match. So for mass production, it's unlikely to ever happen. So molds are always going to be there and molding is always going to be there for mass production. For job shops, few of parts maybe they could be 3D printed. So if you say racing car, maybe yes, racing car shell can be 3D printed. But when it comes to people's car, the parts have to be, the plastic parts have to be molded only. Only yes, some contribution of plastic can be there in probably pattern making, which will make probably the process of making casting for the mold a little different way. Okay. Now, with this initial thought, let me start logically in the same order. So, first, let us understand from Dr. Manoranjan about what is the likely trend change in terms of the new plastics which are coming into the field and what are their demands which are different from the conventional demands when it comes to mold making and molding process. Over to you, sir.
Thank you, sir.
I think
Thank you, sir, for introducing all this about. Uh, if we go for the earlier session, Avinash ji has described what is the myth and what is the confusions are there in current scenario, how they are thinking the plastics. Generally, people are thinking that plastics is bad, even if it is not good for health. A lot of things are there. Many people, they raked and they listen these words and they put into their daily life. Okay, they tell their babies and their kids and all, husband, this is not good for health, not that much compatible with atmosphere, environments, all the things, blah, 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 they will tell. But they themselves forget when they come from their home or when they are going by car or when they are going by metro rail, so somewhere by airplane, anywhere. Can they live a single day without plastics? No, it's not at all possible. Even if I'm wherever I'm worrying, speaking here, whatever I'm sitting, there is a huge contribution of plastics. And this is such a material that if you go energy saving and all, metals are alternates are there, but plastics, you cannot have any alternates. If you need any production capacity, high production capacity, suppose you need some development of new color and design and aesthetic looks, lightweight, energy saving, then only one alternate there is plastics. Just one example, we all agree that metals is a just like a iron. I can example give you iron. Everybody knows there is a what is the applications of iron, how they can use, and what is the benefit. Same iron, suppose we make a knife and push somebody, that is bad for them. So the innovation, whatever we go, whatever the things we develop from plastics, that is we and the our means peoples are there, how we are using that. We are taking a plastics wrapping, single-use plastics we are throwing somewhere. We are not segregating properly. We are not doing properly what are the methodologies are there, how to put it recycling. Many times you can recycle by getting the same properties. But instead of collecting the plastics and segregating the plastics, we are simply throwing here and there. Many people has the idea that there is a commodity and common use, just like bucket, carry bag, that's all. No, it's not like that. Plastics are huge applications. There is a lot of innovation. If you see all research and development in current areas, I meant to say here, 90% are research are doing on plastics. You can see in mechanical guys doing research in plastics. Electronic guys without plastics, they cannot do any research. Electronic items, anywhere, we can go without plastics, they cannot do any, all 90% of research, even if every streams they are coming toward the plastics because they know what is the benefit. Just Shah told one example of 3D printings and all. This is going to a boom because of plastics are there. It is easily, we can melt it and make it 3D printing designs and all. But the new development of plastics are there. Nowadays, leave only polyethylene, polypropylene, lot other alternatives are there. Just like engineering plastics, specially graded of plastics, just like polyether ketone, Teflon and all. All varieties of engineering plastics are there in the market. We need to understand whatever plastics and how we are using. Suppose you have a mold design and mold technology are there. Whenever we are printing, example, I am printing a 3D printing, I need to select a materials. So people should know about the applications and as per the application, how to choose a plastics. It's not like that I can use same plastics for all applications. So suppose I'm going for engineering applications, I need a different grade of plastics. That is why before doing any design aspect, all designers and all experts are here, they know. Without know this shrinkage value, without know this material behavior, without know the properties, we cannot select a plastics. So once we know these applications, our criteria, what is the dimensional stability, shrinkage value, even if the flow behavior, even if the metal properties, then only you can select the plastics. And that is very vital to select a proper plastics for a proper use. If you see recent advancement, a lot of recent advancements are there. For example, printable plastics are there, then biodegradable plastics are there, composites metals are there, blends and alloys are there, nano composites are there. So these are all categories of plastics. A common name is one another example I am giving here, the biodegradable or compostable plastics. Okay, one because this is recent developments are going on, and in 3D printing we are using PLA, polylactic acids. And other nylons and other grades also there, but commonly they are using polylactic acids and what is a compostables or biodegradable plastics are there. And currently, because of the environmental scenario, many of the single plastics and all these things are banned. Okay, so we cannot use a single-use plastics. But people knows which is, nowadays also many people confuse which is single-use plastics. The same bottle I can use multiple times. Okay, so suppose somebody, I can tell bottles I can use multiple times. So it is not a single-use plastics. So there is a, again confusion, which is single-use plastics, which is not single-use plastics. There is a confusion. So generally concepts when we use once and throw, that is known as a single-use plastics because we are not doing means again and again. So small bottles. If it is a 1 liter or 2 liter bottles, okay, we can use many times. But small bottles, just like we are doing here. So in that case, what are the alternate plastics are there? We are doing, and CIPET is a, I belong to CIPET, and in our organizations, we do many certifications and testings of plastics products, which is compostable. Then many people has a tell that suppose this is a compostable plastic. Suppose this is a compostable plastics or biodegradable plastic. So I can throw it here, say let it be compostable. So what I will do? Suppose I will put it here. Suppose this is degradable, then what is the use? There should be a proper understanding. Compostable or biodegradable plastics is not like that anywhere you can throw, it will be degraded. It's not like that. Just like carry bags and all, whatever they are, suppose you go any market or DMart or any suppose shopping malls and all, what are the bags you are getting? Same bags in the name of compostable plastics we are buying and throwing anywhere, it is not going to degrade at all. It will take times. It is more dangerous. These plastics are only compostable under certain conditions. We have to put some conditions, just like a moisture, soil, compost, carbon content, nitrogen content. In that condition, suppose you are putting that plastics, then only it is degradable. So that type of confusion, whatever in our mind, it should be avoided. It's not like that anywhere you can throw. Then also challenges are there. You can see in the market and you can see, sometimes people tell it is biodegradable, it is compostable, it is non-degradable, it is oxo-degradable. Okay, many terms are there. In India, as of now, compostable standard is there, which is we are using for composting conditions. So, oxo-degradable, suppose like films, another example, I am taking oxo-degradables. So, whatever the polythene pouches and all we are using, even if in your rooftop you are using the films, okay? And whenever we are putting the films on the rooftop, you can see UV exposures are there, lights are there, weatherings are there. So after some times, what will happen? It will fragmented. And maybe after 2 years or 5 years or 10 years, we are not able to see what is happening. It's not visible. Shall it be biodegradable? No. Shall it be compostable? No. It is only non-visible to us. It is fragmented. And this is again a major concern, which is nowadays people are telling microplastics. I think many people have heard about that. Microplastics. This is only the fragmented part of the plastics, which is again captured by the soil. It goes to the river body. Indirectly, it will come to our health also. Whenever we are drinking waters and all, that is more dangerous. So, in our research opinion, I will tell. Suppose you are using a plastics, better to do recycling. Recycling is the best option. If you don't know what is degradable, you don't know what is compostable, you don't know what is oxo-biodegradable, instead of avoiding all this terminology, better to have a recyclability. Because recyclability is very known technology. Many industries are there, many people are there, they are working on the recyclable technology. So this is the best option. So instead of, suppose you are telling oxo-degradable, again it will, some points are there. We are not able to know where is the plastic, where it has gone. There is a standards are there, Indian standard is there, national standard is there, European standards are there, the standards are doing. But first to say recycling, then any alternative is there, we can go for the compostability studies and all. So this is the new invention again in the areas of compostability and other things. So it's okay. So just one I'm briefing. So better to have an idea of polymeric material before to going to any application. Suppose you're doing mold design or any design aspects and all. If you know about the plastics behavior and plastics characteristics, that anything can be used and it is not a hazardous things. As it is told, it is a carbon linkage only. It is a chain only. It's not like that. We can. Why I am telling here? Don't tell your childs and all. This is negative things and all. You can say. You can either teach them. Collect this, see to their recycling unit, send them back, make a value chain. Instead of teaching, it is banned. It is hazardous. So this type of things I mean to conclude here. And again, rest of the things Avinash sir will tell.
Some more questions. I will not leave you so easily. Sir, there is a general notion that while you can recycle plastic, thermoset you can't recycle. But we have learned that there is something called as quasi-thermoset, which can be recycled, which can be not remelted, but it can be disintegrated and made into another product. So one thing is if you can throw some light on that one. Secondly, I will combine two questions. the main problem, as I see, why plastics have got a bad name are for two reasons. One is, as you say, that because of microplastics and fragmented plastics which cannot be collected for recycling, that is one problem. Other problem is that we have 7 variants of thermoplast also, including the biodegradable one. Now the thing is, there is a mix up and nobody really knows which is which. So if somebody can segregate them category wise, then probably it will be much easier and economical to recycle and reuse it. So if there are some changes in the way we are sold plastic and the way we throw it in, if the plastic products bear at least the type of plastic marker, like what grade of plastic it is, so that all similar can be pulled together even by a layman. What's your take on that, sir?
Sir, I'll go to your first question, thermoset and thermoplastics. Everybody knows what is thermoplastics and what is thermoset. Thermoplastic simply you can remelt and again you can get a product. But in thermoset, once it is got a product, it is very difficult to get it again remolded. Okay, simple words to understand. So that is again a big challenge because nowadays many glass fiber reinforced plastics. Okay, then thermoset just like a pressure cooker handles, printed circuit boards. These are all thermoset type materials. Yeah, I understand that it is not recyclable, but nowadays what they are doing, that is taking their crossing, they are grinding into the finer particles and making them used as a reinforcing agent. We are using in many plastics, just like example of polyvinyl chlorinic PVC pipes, we are using calcium carbonate, okay, and we are using as a reinforcing agent so that the pipe and all that properties will increase. So there is one option when there is a thermoset materials, we have to make it collected in properly. There is many grinders, many things are there, we can pulverize it and that can be used as a reinforcing agents. Instead of using all types of glass fibers and all, you can use it as a reinforcing agents and that can be a one benefited. Anyhow, many of the plastics on nowadays, there is a, because thermoplastics, it is okay. In case of thermoset, another challenge is the glass fiber reinforced plastics. Just like a wind power mills and all, the blades and all, the composite bodies are there. There is all epoxy with glass fiber or carbon or glass fiber. There is a combination. Many people, many research, many articles are there, but as of now, there is no concrete solutions are there. Though research is going on, but there is a major challenges and people are doing in this work. As of now, one solution is there to reinforce it again and go to the new products. This is one. And regarding this second question, so because plastics, categories of plastics are there. Polyethylene, polypropylene, PVC, nylon, ABS, HIPS, thousands of categories are nowadays developed. As Sir pointed out, it's very difficult to identify a plastics easily. It's not that much easy. All the plastics has different behaviors. Some plastics has a different melting point. Some has different means flow behavior. Some has just like injection grade, extrusion grade, flow grade, different grades are there. Collection is a major challenge. So, as of now, as per the Central Pollution Control Board and Ministry of Environment, they have given some coding. So, recyclability code 1, 2, 3, 4, that is there. So, by seeing the coding, even if we can see like this PET bottle also, PET, there is a recyclability coding is there. So, by the coding, we can identify, there is one option. And second is some identification methods are there. If you go and search through Google's, you can get the solution also. What is the behavior? Suppose I put it some in water, some plastics. So whether it is dipping or it is floating. If it is floating, what type of plastics? If it is dipping, it is what is by density separation, by melting point. There is a awareness is required among the people to identify the plastics. Once plastics is identified, there is no problem at all for the recycler and for the development of new products also. Last point, Sir told, if it is mixed with the biopolymer, suppose people are telling this plastic is compostable and they add some percentage of polypropylene or polyethylene. So people, they get the certificates. So they get the certification from Central Pollution Control Board that my product is compostable, but later on they add some other material, 10 to 20% they can add and they can say, okay, this is compostable. That can be easily identified by simple identification methods are there actually. In CIPET we are doing. So by FTA or DSC simple 2-3 analysis are there that can be easily identified. And if they are adding 10% or 5% also into the biopolymer, that is not going to degrade. The value will change. So identification techniques are there, not to worry. But we need to integrate the people in a common platform and to make them aware how to identify the plastics, how to know about the plastics. The rag pickers who are collecting the plastics, let them know how to segregate all. So this is awareness is required, sir.
Further to what Doctor has said, I have seen one solution developed by Fanuc. They have a robo with a vision system, which is sitting on the conveyor that is carrying the scrap, say mixed plastic scrap, let us say. Now the vision system identifies the objects like bottle or something, and with AI algorithm it knows that this kind of object, what is the grade of plastic. So instead of going chemically into the plastic identification, from the object level, you can teach in through AI ML and you can do a pretty good job of segregation. That's one solution. Yeah. Yeah.
Means, last, before I think 2019, we have been to Switzerland, some means European country. CIPET team has gone and visited many places. Segregation methods, they are told if there is a conveyor belt, plastics are moved like this, some IR radiations will be there. From IR radiation, you get to know what is the plastics, P, PP and all. So once this flow is there, the radiation will flow and automatically it will reflect and that will be segregated. So the technology is already available. In India, it's a bit difficult because cost is more, sir. Very, very expensive. In India, manpower is less cost. We have plenty of manpower. So that is why, as of now, I have not seen any industry to do laser techniques because of the cost and all. But that is a good techniques where you can segregate the plastics to go for the recycling techniques.
Now again, as I said in the previous session, it's a question of scaling. If many people start buying these technology solutions, probably the cost will crack down and it will become affordable as well as viable. Okay. Now I'll talk to the next speaker about the molding part, about the mold part. Sir, with the advent of new plastics, have you observed that there are some changes in the design rules for the plastic parts or for the design of the mold itself in terms of the tolerances or the process window, parameters, etc.?
This is working. Thank you so much. Thank you for having me here. This is Lokesh. Are there any new design rules for design for manufacturing? It's very industry specific and each industry would choose its own level of, but if you ask me as a general engineer, I think the rule should keep changing. We should never ever stay stagnant and pushing ourselves to the limit and pushing ourselves forward is very important. That's how I would respond to it. And do we go to the next point also straight away? On to there? Thank you. I really here, thank you so much for having me here. I would really like to talk about holistic design. Holistic design. And I understand this is a very august audience. The top mold makers in the country are here. And also, if I may just say so, one of the senior most die casters in the country, Mr. Shivalingam, is sitting here in the audience. He was into die casting even before I was born. Sir, please raise your hand so that the people know that you're here, sir. Right. To go on, I would just quickly like to go through what I mean by holistic design. And of course, one can also expand on this concept. We have basic product design, we have component design, we have die and mold design, we have runner and gate design in the mold itself, we have machining and fixture design, and design readiness for machining. I would like to bring your attention to 2 points here. One may ask, what is the difference between product design and component design? Just so that there is no, shall we say that it is a very fuzzy line, and to the one side we have functionality and process ability. The other side is the component itself, which is supposed to be efficient in its design. That's how I would separate between product and component design. Then there is die and mold design and design for fixturing. Now, we find, I'd like to take the examples of two Japanese companies, Sanyo and Yamaha. Now, what Sanyo did, they were just a specific design house, right? They had specialists in plastic design, they had specialists in die casting zinc separate, aluminum separate, and steel separate, right? But anybody could go to them and give them a job. So the component was designed by a process specialist with the design elements in place. It was not designed by the person by the original company. Like for instance, Toyota's most famous engine, the VV2, was designed by Yamaha because their design capabilities are way superior to what Toyota does. And so when you go to a specialist for a particular design, you get a way superior product. And once that happens, and very often, I think Mr. Shivlingam will also say he's dealt with thousands of components in his lifetime. Very often, we look at a die casting component. We know it has been designed by a draftsman and not by a die caster or another person. And the die casters are struggling to bring quality into the part. The die becomes so complicated, and we are constantly suffering with quality problems. Why? Because once you make a drawing, it is cast in gold, it is etched in stone. You can't change it. You need 20 different permissions before you make even a small change in the drawing, right? But if that much thought had been put right in the beginning at the component design stage, then we could have ruled out, right? He can imagine how the molten metal is flowing, right? And then put that straight into the part in the design a chassis for the part, and go to the functional elements and just put it together. And the minute you do that, there is clarity in the mold design, there is clarity in the fixture design. You're also able to think of how to make the component fixture ready and fixture friendly. So that's roughly what holistic design would be. And I have a few other points, but...
Sir, one more question. That when we look around the market of software ecosystem that is supposed to support the design of plastic parts as well as design of molds, one comes across several simulation software and CAD-CAM kind of a software to support the manufacturing. Now, but my observation, and I may be 100% wrong because I am a distant observer from this domain, that Indian industry tends to think these softwares, the use of software as akin to मच्छर मारने के लिए मिसाइल का प्रयोग करना. So, and they do all their processes by thumb rule based design. What's your take on that, sir? What's your experience?
I would like to start by, getting software and getting the license is one thing. I know hundreds of companies that have the software, but very few people to actually use the software to its full capability. So getting the people to run the software is very often missing. And then you buy the latest software, you hardly use 5% of its capability. That's one thing. But having said that, we know that every version of the design software that is coming out today, from the component design point of view, is so amazingly good that when the designer is sitting there in front of the computer, exactly what he imagines is the software is able to translate. So it's a really it's heartening to see that kind of thing.
So with the product requirements getting more stringent in terms of quality and complexity and repeatability, etc., do you foresee the forced necessity of using these software going further?
I think it should become more stringent, right? We tend to have this, I don't think we Indians have gotten out of our colonial attitude. We just believe that something that comes from either Japan or Germany is superior. It's not. We are on par with anybody, and it's high time we got out of that. I think we should start doing design in-house. It doesn't mean that we'll get it right the first time. It's okay. It's an iterative process. You change, you make 5 mistakes, go through the next one, do it right. And once you build that capability, we are top notch, we can be cutting edge. I think we should put tighter expectation out of design itself. Use lesser material, bring the cost down to absolute minimum, don't waste raw material anywhere in the part, bring it down to its most optimum best. Of course, put all your fatigue and creep and every other long-term thing into it. But really, I think we should just become tighter and push it more.
Sir, the aggressive requirements that are being forced in the plastic parts nowadays are micron tolerances, excellent mechanical properties comparable with metals or maybe better than metals, and spring action in plastic parts, use of thin sections in plastic products. So, with all this, what are the changes in mold making that you foresee?
Would you like to take this, or isn't it better handled by you? Or
Yeah, this plastics, whatever that strength, this is a measure criteria. Then again, flowability. Suppose critical designs are there. Just like a mobile back casing is very thin, and if you choose a wrong parts, then it will not flow. So definitely there is a requirement of this mechanical strength, because people nowadays they want to replace metal to plastics. Many of the parts they succeed also, and many of the developments still going on. So this can be done, but up to a certain extent, because you know majority of plastics, metal, just like metal, we don't have that much melting temperature. In case of plastics, it's roughly 600, 700 degree maximum can go, whereas metal more than thousands. Strength wise also it's bit there, but however many new plastics are came into the market, at least comparable, we can say, that is comparable to some extent. But anyhow, dimensional stability and other things is play a major role. That I agree. So I have to take care of all these things whenever we're taking a mold design and all.
There's a question that you had put earlier. Shall I just respond to that
Oh, yes,
also?
please.
So I like the way he framed the question. Are textures being used wholeheartedly, or are they being treated like cutlery? And I thought that was a very well worded question.
Now, I was asking that nowadays there is a new technology in vogue, that is laser texturing of molds.
Also,
Now,
yeah.
if you want to have a bottle and here you want to have a rough surface finish so that you can grip the bottle. Now, the mold you have to subject to laser so that you have a matte finish. Now, you have a matte finish by laser texturing, but does it affect the functionality of mold in the sense that the mold release compound and how it will come out, and like what kind of draft should be there? Now,
Right.
what's your
So,
take on that?
as of now, with the kind of steel technology that we have, even with, say, Daivar or Udahome or 2367 or any of these top end steels, you see, flowing molten aluminium, unlike plastic, is extremely aggressive, right? It will just, the eddy currents formed while the molten metal is flowing is so strong that it will just very easily erode away the texturing that you give it. So, texturing in die casting is not something that will last very long. If the life of a mold is about, say, 100,000 shots, texturing won't even last 5-10,000 shots, right? And then there is a degradation in this. So that's not a very, unlike in plastic where it's much more mold friendly, it doesn't lend itself to, we don't have the technology today, even with the latest coating processes. We don't have that technology. So that's a bit of a thing. But coming back to your fixturing,
Fixtures are being treated as cutlery item. Means if you use it is fine, but if you don't use also, most of the time you choose not to use it.
That's
Like
one.
we eat by hand.
And the other thing is that fixtures are usually put in place either to please the customer or to please the ISO auditor, not so much as an internal requirement from the industry itself, because there are multiple benefits of productivity, bringing down defects, and the quality control at a very large level. Fixturing is the way forward. And it takes the human element. You can keep the person, but still take the error element out of the human using a decent fixture. So, yeah.
And automation is severely limited unless you use fixtures for things like degating, for things like, of course, for trimming you are using fixture, but for dropping the hardware, the snap-in kind of nuts, etc., pel nuts or what you call them, the nuts which snap onto the plastic sheet, etc. Now, there is a lot of room for advancement in fixtures, the application of Industry 4, the application of electronics, I mean, tying up with automation. So, it gives a huge scope for productivity improvement. Okay. As IMTMA, I am doing training on fixtures for plastics. You are welcome to come to our training if you want more details. But we'll move over to the next speaker. A lot of hoopla is there about metal 3D printing. Now, metal 3D printing, how it is poised to transform the way the molds are made. So, what's your take, sir?
Hey, good afternoon, everyone. Am I audible? Yeah. So, any technology for that matter to grow, first of all, there should be users of the technology. And that is a big hurdle most of the time, as you said. It is a matter of scaling also. So again, as sir mentioned, choosing the right material is one thing because the application has to be successful. Designing that application has to be wholeheartedly done. It should be a holistic design. The tool, the component, everything around it, the ecosystem, and even the technology has to be designed in such a way that it complements what is the real output, what is needed by the customer. And that is where 3D printing or additive manufacturing as a technology generally comes in. There is some sort of a stigma that, okay, this is here to completely replace or the traditional manufacturing, which is not true. Majority of the time, this is a complementing technology which adds value to what we have been currently doing. So in the case of, let's say, mold, we all know conformal cooling can really impact mold and die for component quality levels in order to get the die casting dies to last longer because the thermal impacts are reduced with the conformal cooling. And even I was a mold maker myself about 10 years back. And then when we were designing, so I came across 3D printing in the form of conformal cooling. And I was like, wow, why people are not using this? There is a very good chance.
Sorry to interrupt. Just
Yeah.
for those who do not know the word conformal cooling, let me explain it. See, parallel to the curved surface of the mold, you embed some cooling channels inside through which coolant can be flown so that it cools the mold surface effectively and much faster.
Yeah.
Okay.
Thank
and
you.
it affects quality as well as the cycle time.
Thank you. So most of the time what happens with the general cooling channels in molding, you all know, it is conventionally drilled and plugged and it won't reach into the extent of all the critical and complicated part geometries. What conformal cooling provides is, as sir mentioned, you can just from the surface level of the component, you can follow the same contour and same path of your component and you can have a much effective cooling. This will reduce the thermal gradient of the whole surface, which is in terms a very good quality thing for the parts to be produced. So generally in plastic plastic molding and also in die casting, one of the bigger challenges is the thermal gradient of the entire part. One side it cools down, the other side is still hot, and then we use fixtures and cooling fixtures, all the things to get the cooling going on. Whereas from the mold itself, if we can cool it down in a faster, more efficient way, the quality really improves. And this is where majority of the time additive manufacturing is used in injection molding or die casting to make the inserts, the core and cavity inserts, along with conformal cooling. What is the challenge? It used to be a very costly affair. I'm purposefully saying it used to be a very costly affair. And the problem is once people are thinking that it is a costly affair, then they kind of shut their blind eye to that and think that okay, this is extremely costly. But the advancements have happened in the technology so that earlier days we used to make this 3D printed inserts by putting a powder of 20 micron, 20 micron, 20 micron. Nowadays there are quantum materials, like we have 100 microns of layer coming in with the same surface finish, and the build rates have come to a level where 400 grams or even 800 grams of material can be melted in an hour. Whereas earlier it used to be something like 50 grams and 40 grams and things like that. And with the help of multi-headed laser, the things have become even more attractive. So we had some cases where the tire mold manufacturers, for them it was very important to produce the tire molds in a much faster way, because that is where the technology and their realization time is pretty long. And the tire mold segment itself is very huge, and that is another limitation of 3D printing, where the machine sizes are relatively smaller. And what they've been doing is they've been printing the tires as segments, multiple segments in one 3D printing machine with multiple laser heads. So the printing time is actually coming way less, and there were cases where we were able to produce an entire segment within 72 hours. An entire molding segment with conformal cooling channels for a tire mold in 72 hours. Then it comes to the tool maker to come and assemble and everything and then prick it. So the technology is there, and again how we are embracing the technology, how the industry is pushing that technology to come to the level of cost effectiveness, and what is the cost expectation and things like that. Another thing, as doctor said, the material choices. For each material, we traditionally use the typical cold and hot work steels. Then is there any material where we can kind of push the limit? Is there any software where we can design in a much better level? So majority of our 3D or the 3D modeling softwares are from a traditional manufacturing idea. There are recent developments in the software field itself, like softwares like N topology, softwares like Hyperganic. The software like Hyperganic doesn't even have a CAD or a GUI at all. It is completely based on coding. So it is not related to how a design engineer is thinking. He is setting his parameters, this is what I want, and then letting the system run through multiple iterations in a flash of a second to provide him multiple design which he is not even imagining from his real level. And that is where the softwares are reaching. And of course, then the softwares are producing something which can only be either 3D printed or converted using such advanced manufacturing technology. And the more we embrace it, the more we show our affinity and passion towards it. And this is all important. Selection of material, wholehearted design. And design, I will tell you, I was a designer 10-15 years back, and the way core and cavity is being extracted is still the same even now. There is no change. Absolutely no change. You pick up a polymer material, you decide that okay, this is going to be my part, and then design it. Then let the software decide where the drafts are needed, where the parting line is needed. That's it. Absolutely no movement on that. But in the design of the mold, in the design of fixtures, in the design of the ecosystem, there have been improvement for sure. As sir said once again on the fixtures, the reason why we are not using fixtures to a great extent is that it is again thought as an afterthought. Why do we need it? And then the fixtures are also like, okay, you conventionally machine it, manufacture it. It is also a pain. There have been advancements again in the fixture set on, okay, how can we have multiple segments of fixture in a much faster way, in a much cost-effective way, and we can even use it in a better sense. And again, then comes the question of sustainability and question of degradability. Where is this material going? In polymer, the stigma around that whole thing. Do we even know that from plant beans, 3D printing powders have been produced? The same powder can be used even for molding if you melt. And then that is happening in Rajasthan. Actually, the company is Arkema. They are from a US-based company. They are making the powder from a plant, which is like, okay, you can farm a lot of plant. It is not even affecting deforestation. You're not cutting down tree or anything. You're planting a lot of, you're farming a lot of plant. You're getting powder from it, which is biodegradable. It is a P11 powder. This is P11 powder is coming from a plant. So people who have that stigma about plastic being an alien material, that it can be such an organic stuff as well. So there are most of the time the technology, the implication of technology, I would like to use a small example. AI, the moment we say artificial intelligence, people are kind of afraid because the news what comes is more like from deep fake and how a lot of regenerative stuff happens without our own limitations and how it can screw up human life and things like that. But the same AI can be used to check whether that photo is a deep fake one or a regular one. So technology is always there. It is about the users, how to use that in a much better sense. And this is where everything evolves.
Hello. Hello. To add to what he has said, see, the problem starts with mechanical design of plastic parts because our mechanical designers who are designing, so let us say, structural elements, they know how to design with a homogeneous material. But given the fact that with plastics and with composites particularly, there is a possibility of tailoring anisotropy and tailoring strength, and there could be a differential strength across the cross section. So how does one do mechanical design with such a material? Now that art and science and curriculum has to really evolve. We have to have experts who know how to design with material like that. So that's one of the problem. Coming to my next question to you, 3D printing, for metal 3D printing is accused of two, three things. One is that the largest size of machine that is available, the machine table, is just about 400 by 400. But your molds are probably much bigger than that many times. So how does one go about it? That is question number one. Question number two, that again there is a problem of porosity, anisotropy, layered anisotropy. People think that if you hit the hammer sideways, it will just cleave because the bonding between layers is questionable. And if you do hot isostatic pressing, then there is shrinkage and distortion and everything. So either you have simulation which accounts for all those and compensates, or it becomes difficult. So what's your take on that, sir?
Yeah, it's an interesting question again because of the 3D printing again. Of course, size is a big limitation. Right now, 400 by 400 is the mostly known as the biggest size. Though there are multiple OEMs who are trying to develop 650 by 650 into 1 meter height and things like that. Of course, 3D printing an entire mold itself is, to be very frank, it is not a cost-effective solution. Again, from a core insert, what part of the core insert, or is it just the component area alone which we can add on to a conventional part? We call it as hybrid building. Most of the time the hybrid buildings are very easy. And then comes the second question, how about the stability of the part and what about the strength? 3D printing has come and progressed a lot way in the last 3-4 years, especially in terms of material. The porosity levels of a 3D printed part, the defect percentage is hardly 0.03 percentage. It is 99.97 percentage dense in majority of the cases. And you also get complete polishability with certain material where you can even achieve mirror finish in 3D printing without any pore dot or nothing on that. So that is possible for sure. Technology has matured into that level where the materials like 1.2079 or H11, H13 in our regular language, and even CM55 cobalt-free die casting material, all that material possibilities have come so that on the quality of the mold which has been printed, on the mechanical properties about the being an anisotropy and all those things, that question has been can be answered by, I think, almost all OEMs right now. And the interesting fact with the softwares is that again, we have seen an experiment with N-topology where they were trying to reduce the footprint or the weight of the entire core insert. Typically, the designer will go for a thumb rule. If it is a 1 mm thickness part, I need to have this much as my core insert. If this is 1.5 mm thickness and if this is this material, depending on my die casting pressure and the mold pressure and things like that, okay, I'll have it. But the reality is that the entire insert is not having that kind of impact loading and things like that. So we do an FE analysis see where the stresses are more, preserve material in that area, and then remove material and add lattice structures to the entire body of the core insert. The benefit is the usage of the material has come cheaper, it has become less. The stiffness of the insert is either the same, we can even increase the stiffness if we use special purpose materials, and at the same time it is becoming economically viable because the printing time is cheaper, less material to build, less material to consume. So there are technology coming into that level, and the situation is that this whole cycle can be a repetitive design workflow. Yeah, the workflow can be set, and then irrespective of any mold insert that you load, and you say that, okay, these are my pressure points and the tonnage of the machine, and some parametric can be given, and then automatically it will give you an analysis of, okay, what is the current FEA level, and then if you do the topology optimization with the lattice, then what is the FEA level. And then while you printing, there is also a lot of simulation software. The advancement of process simulation in 3D printing itself has come to a level where people can start predicting what is the thermal situation of the entire mold, where the isotropy can be changed, the microstructure can have an impact, and all those things. It can be easily predicted by the process simulation software. It has come to a level where the maturity is also come, where of course we can understand, okay, what is the mechanical warpages, and then what is also the thermal impact of the whole thing. So to answer this, even the hybrid printed part, there was an experiment where people kind of printed tensile coupons. So the bottom part was designed, conventionally manufactured, and then on top of that 3D printing has happened. And then it was exposed into the testing, and while the breaking point was still not the boundary between the conventional building and 3D printing, the breaking point was still where it is supposed to break. So the mechanical properties of the 3D printing insert has come to a greater level. Even in titanium, the hot isostatic pressing or hipping in a regular manner, it is very widely used technology, because titanium 3D printing or titanium casting generally tend to have a lot of porosity. We have defined a process recently where after printing, you just have to do the regular heat treatment. You don't have to do the hipping. You still get a fatigue strength of 600, which is commonly accepted as a fatigue property even after this hipping. So directly from the printing itself, if you are tweaking the process, tweaking the material, selection of all that is very important, we can come to that level. So the technology has taken drastic leap in the last, let's say, 4 or 5 years, especially in the 3D printing world. If you have been following the 3D printing industry, the last 4 or 5 years, the leap with all that surgeons in the innovation is very high. And that is what showing in even India. If you look at, there are a lot of Indian 3D printing machine manufacturers coming up. Earlier it was not a possibility because people thought it is an extremely costly solution. And that is just, as you said, it is, to kill a mosquito, we are trying to use a missile kind of a situation. But right now it is not the case.
So with this, we do wish, and it's a dream, that our mold makers will consider additive manufacturing technology going further in designing and manufacturing of mold in a bigger way. And hope it will come soon. Well, thanks for your attention. You have been a wonderful audience, and has been a wonderful discussion. I personally enjoyed a lot interacting with these expert panelists. And bye bye, best of luck, and thanks to Messe Stuttgart for giving us opportunity to bring out our thought process here.
Heartfelt thank you to all our esteemed panelists, Mr. Avinash Khare, Mr. Manoranjan Biswal, Mr. Lokesh Naik, and Mr. Andrews Lejoy, for sharing profound insights with us during that enlightening session. Your expertise has significantly enriched our understanding of technological innovations and its global implications in the molding industry. Now I extend an invitation to Mr. Lokesh Khare, Division Director, Messe Stuttgart, India, to join us on the stage to honor our distinguished panel of speakers. A warm thank you to Mr. Manoranjan Biswal for offering your valuable perspectives. Thank you, Mr. Andrews Lejoy, for your meaningful contributions during this panel discussion. We would also like to thank Mr. Lokesh Naik for your detailed insights. I would request the audience to kindly give a big round of applause to the panelists for the insights that they shared. Mr. Lejoy, please join us. Thank you so much. And lastly, Mr. Avinash Khare for effectively guiding us through this enlightening session. Mr. Avinash Khare, the moderator for this session. Thank you, Mr. Khare, and congratulations once again to our esteemed panelists. I would request all the panelists to kindly pose for an official photograph.